everyone. Thank you for joining us. I'm Kathy Wells, editor of OEM Off-Highway magazine, and welcome to day 2 of OEM Off-Highway's second annual OEM Industry Summit, the premier educational event for off-highway equipment designers and engineers. This event is made possible by our platinum sponsor, Volvo Penta. Volvo Penta is a world-leading supplier of premium power solutions for off-road applications all over the world. With a combination of strength and versatility, Volvo Penta engines supply industrial operations with durable and reliable performance. Throughout the course of the summit, OEM Off-Highway magazine, our session sponsors, and our expert speakers will deliver 9 sessions covering a range of topics. All sessions are being recorded and will be available on demand to registrants. Be sure that you're registered for any or all of this week's sessions at oemoffhighway.com/webinars. A couple of tips on the platform before we get started. Our presentation today will feature slides with live audio from our presenters. You'll note that your view within the system is customizable, so please feel free to tweak or adjust the layout and engage with different windows to meet your viewing preferences. Following today's presentation, we'll begin a live Q&A. We encourage you, of course, to use the Q&A box on your screen to submit your questions to our presenters at any time, and we'll answer as many of them as possible. This Q&A box is also where you're welcome to contact our team for assistance with any technical issues. And last but not least, please be sure to check out the related content section for some additional information and resources there. Now let's get things going. We're happy to have you all here with us for the last session of our day, examining ISO 13849 safety standard and what it means for off-road equipment OEMs, presented by Rich Nagel, Jonah Leeson, and OEM Off-Highway magazine. This session is sponsored by Parker Hannifin and will discuss new provisions for software safety requirements. Parker Hannifin is a Fortune 250 global leader in motion and control technologies. For more than a century, the company has been enabling engineering breakthroughs that lead to a better tomorrow. At this time, I'd like to welcome our speakers for this session, Rich Nagel and Jonah Leeson. Gentlemen, thank you for being here with us this afternoon. I will now officially hand off the controls to you guys to begin the presentation and have you share a little bit more about each of your backgrounds. I think let's start with you, Jonah. Go ahead, take it away.
Hi, I'm Jonah Leeson. I'm the product manager for electrification at Parker Hannifin. I'm based out of Rohnert Park, California, and a part of our EMC division. I've got more than 18 years of experience in various technical and commercial roles in primarily the commercial vehicle space. And I've got more than 9 years of experience with electrification. Rich?
Yeah, and good afternoon, good morning. Rich Nagel, also with Parker Hannifin. I'm a program manager for our electrification growth team, which was formed a little less than 2 years ago. I'm a boomeranger with Parker. I've been here almost 30 years. Grew up on the industrial hydraulics, electric hydraulics, factory automation side. I spent about 8 years as a marketing director in the commercial vehicle sector, and I came back a year and a half ago to work on mobile electrification. And it's really exciting, and we're all learning every day because it's a very dynamic business. And thanks everyone for tuning in today. All right. So obviously we've got a little less than 30 minutes, and ISO 13849 is a very complicated, functional safety is very complicated. So, we're going to do our best to give a high level overview. Once again, we tell everybody it's complicated. It is not an easy subject, which is probably why we have a lot of interest today. It's part of an overall machine safety strategy. And we'll get into some of the definitions and how it affects hydraulic equipment. We'll give you a couple examples. It's not legislated. It's a global standard that in a process, a lot of emphasis on process that governs the safe operation of electrified mobile machinery. And this is just a high level overview of how it plays into the overall process. Obviously, we're a hardware supplier, so we have one perspective might be different than some of the actual OEs, but we'll kind of walk through from our viewpoint. So, of course, what it's not, it's not one thing. I think, sometimes we like to look at these as, check a box and move on. It's a methodology. There's a lot of things in the methodology, how we evaluate and achieve safe machine operation. One of the things we'll talk about from our vantage point is safe torque off, STO. We use that term a lot in our industry. It's just one tool in an overall safety strategy. And, we like to say ISO 13849 does not reside in one device, but one device can support the implementation of ISO 13849. So it does go into the design of the product along with the overall process. So at this point, we have to demarcate ISO 26262, and it always comes up in every conversation about functional safety. I use the Venn diagram from like second grade math, right? Because we have off-highway and on-highway. And of course, we have this overlap because in on-highway, we have a lot of electrified hydraulic applications. And so, what ISO requirement governs those operations is always a topic of conversation. And so, from our standpoint, we're looking at primarily the inverter or multiple inverters on a piece of electrified mobile equipment. We've got things like external sensors that provide information to the inverter and a machine controller that kind of governs the overall hydraulic and system operation. So when we talk about safe torque off, that's really resides in the inverter. We'll go through some more detail. And of course, this inverter for most electrified equipment today is operating a PMAC, a permanent magnet motor. And of course, that converts DC power from the battery to three-phase to the motor. Safe torque off removes all the electrical energy to the motor. So the motor to the inverter, we have to take all that stored energy out of the system. I use a hydraulic analogy. If you have a hydraulic accumulators in your system, there are ways that you have to do and requirements to vent power out of that accumulator. And of course, depending how you do it, you can have a lot of stored energy. And just like an accumulator, you can get a lot of instantaneous flow. With safe torque off, you can have really high peak current values that you have to deal with on the inverter side. Jonah, I'm going to hand it over to you to talk a little bit about process methodology. Thank you.
Yeah, absolutely. So one of the things we'll note is that there was recently update to 13849 this year in April. And they really tried to solidify some of the concepts. So we're going to walk through the steps. I'll just briefly touch on some of the differences between this new revision or this new edition. For the first one, defining safety functions, they really suggest multidiscipline risk assessment to inform the safety requirement specification. So there was not a lot of verbiage in the prior edition for that. Step 2 is determining the performance level requirement. So a lot of us you probably signed on because you've heard of PLA, PLB, PLC, PLD, PLE. That's the performance level requirement. And there in the 23, they clarify categories, basically reliability as a measure of the performance level in the system or the subsystem. And step 3 is designing and implementing the safety functions. And then 4, determining and evaluating quantitatively what performance level was achieved. And then validation, there's a big change in the validation in the 23 version, basically bringing in more detail and moving it up to the first section of the document. The differences aren't important. The real key here are the steps. So again, defining what your safety functions are, determining what the performance level is required for that, and then designing and implementing, determining and evaluating, and then validating. So we're going to work through some examples. These examples are not intended to be 100% technically correct. As Rich said, the topic is very complex. So I don't want anybody to think that they've solved one of these examples by witnessing this. We're using these as a means to illustrate the process. So defining safety functions. So when we're looking at safety requirement specification, we need to say a high-level description of what the safety function is, what would trigger that, and then what reaction is needed when that happens. So those are the 3 keys. And then from there, we can define what performance level is required. So the 2 examples we see at the bottom of this slide would be preventing an oversteer, where the trigger would be the assist is decreased greater than 25%, meaning I have to steer harder by 25% more when I have a decrease in performance in my steering system. And then what I want to do, the reaction is to maintain decreased performance. And that helps us to prevent oversteer, because then I'm not applying a lot of torque into the steering system that then performance returns and causes an oversteer situation. Another example of this that we'll use to illustrate a little bit later on, and Rich will talk about, is suspended loads, or loads. Basically, if we wanted to, just as an example, prevent an unattended load under positive torque. So if I'm using an electric motor to drive a pump that's providing hydraulic pressure or flow, and pressure is in the system and that's maintaining a load, then if the operator isn't present or leaves the seat or is no longer engaged in the equipment that is suspending that load or holding that load, that's the trigger. So think about like a seat on the switch under the seat of your lawnmower. Your lawnmower turns off when you get out of the seat as a safety method, because it knows that it's a simple switch, but it stops the blades from spinning. It might even kill the motor. Just as an example. So in that condition, when an operator leaves, we want to break the load by another means, meaning we don't want to use the positive torque of the motor to maintain the load in that equipment. So again, description of the function, what triggers it, and then what is my reaction. And then once I have that, then I can get into defining my performance level requirement. So here what we see is that on the top side of the PL, so a PLA, a PLB, those are lower risk functions. And then on the bottom side of that is higher. So PLD, PLE, those are higher. We'll walk through that in the oversteer example. So if I'm looking at preventing oversteer, that means I want to maintain performance in my steering system. First thing I need to decide is how severe is a failure or the opportunity for failure. So if I pick that it's severe and that it could really hurt somebody, or property damage that then affects somebody, then I've made a decision that it's an S2. So it could lead to a severe. So then, now that I've made that decision, I know that my PLR is either a C, a D, or an E. Next, we look at frequency. So this is frequency of occurrence, similar to, and this parallels really the risk analysis that's performed in a DFMEA, where you have severity, detection, and occurrence. So here it's severity, occurrence, and detection. So I've decided that I have a frequent to continuous possibility of exposure to injury. And so I've selected F2, which now means that the system under review or the function under review is either going to be a PLD or a PLE requirement for the function. Furthermore, then we get into the detection. How likely or how possible is it that we'll avoid the hazard? Is it detectable or is it undetectable? So here I've said it's possible to detect it. I have enough sensing in my system where I could sense a decrease in performance, and then I can provide a reaction to that. And my reaction in this case is to maintain a decreased performance. If I lost hydraulic assist altogether, then I don't want to provide any assistance. And that's a function that can be deployed. So now that I've made that decision that I'm an S2, F2, P1. And so that leads me to my performance level requirement being in that PLD area of this process. So what does that mean? PLD. So PLD is not the most severe, but it is. It requires a lot of consideration. If your severity of injury is high, if you're able to detect the failure. So when we look at those probabilities that are defined in the ISO 13849, they give an average probability of dangerous failures per year. So when I pick a D, that's less than 0.1% probability of dangerous failure in 1 year. So if I look at that in 10 years, I've got to design my system so that I have less than a 1% possibility of failure over 10 years for that system. So that's pretty dramatic. And there's a lot of components that go into that. And you have to add, you have to add your mean time to failure calculations of each of the safety related parts or control system in order to derive what that probability is in the system that you're developing. So again, very complex topic. And we just wanted to use these as a way to illustrate how the PLR is selected and then what that actually means when it comes to designing and validating the product or the function within the product. So there's other ways to reduce your PLD. So if you are in control, so reducing probability of dangerous failures. Limiting operation to trained or skilled operators is one method. You may be able to reduce the severity or likelihood of an injury occurring. You could limit people in the danger zone of the equipment that's being operated, but typically that's not a reality for off-road equipment. Construction equipment, there's workers present, but these are just illustrations of means in order to increase safety at the work site or where this machine is operating. We could improve the reliability of the system performance, meaning I have less likelihood of reducing steering assist, meaning I've duplicated efforts, which we'll talk about redundancy. We'll talk about some of the device attributes that could contribute to improved reliability and system performance. I could increase system redundancies. I could build validated reliability into the system that supports the function that's supporting the safety of that vehicle or that function. So when we talk about that in terms of software and firmware, there are methods to ensure that these electromechanical devices are operating safely. So some of the examples here would be lockstep microcontroller unit, dedicating power management, safe real-time operating system isolation. So having the ability to isolate different, the way that the controls are processed on the device, certifying the way that you develop your code and what models you use, strengthen the communication of that device. And then, but ultimately, so as an example, in our GVI, our global vehicle inverters, our software and firmware, we feel comfortable in saying that the probability of failure is less than 10 failures in a billion hours. So that means for that device, the way that we're processing the controls really boosts the confidence that that device is going to be able to control the safety functions safely. And so we've got a very high PLD level in our GVI devices. And that ultimately, going back to what Rich was talking about in STO, we also deploy STO, which we'll talk about in the next slide. So safe torque off is primarily a hardware function. Our device has 2 STO inputs. So those inputs are a voltage, could be coming from a safety controller, could be coming from a high voltage supply to a DC to DC to a switching device. As I said, you know, if we have a pressure monitor in our steering system, that could act as a switch that could cut the voltage, the STO voltage to our device, and that would immediately stop all power to the electric motor from our device. So there's different ways to do it. Our device is not making STO decisions whether or not to turn torque off. Those decisions are being made external to our device, but our device is reliable to ensure that torque is removed when needed in the system, or when commanded in the system, or when triggered in the system. So just to look at that from a functional safety and steering. So steering is a lateral control of the vehicle, which can still be governed because it is a hydraulic function most of the time for steering assist. So what we see here are a couple different architectures. I'm gonna move through this quickly because we're running low on time already. But basically, for a long time, we considered the steering shaft to be a secondary control. So the person behind the steering wheel has a mechanical linkage to the steering, and they should always be able to override the device or override the system and provide steering input. And that becomes, the larger the piece of equipment, the harder that becomes. In some of the off-road equipment, we don't have a mechanical shaft connected to the steering system any longer, right? It's steering by sensing. So there, you really need to look at whether or not you want it to be low voltage or high voltage. If you've selected a low voltage hydraulic assist and you're powering that from a high voltage battery, then you need it's critical on your DC to DC converter that has a high PLR rating so that you can ensure that power is available to power your system. Or you look at redundancy, where if it's a low voltage power steering assist, then you could have a low voltage battery and a high voltage battery with a DC to DC, and you've just applied some redundancy to that system to ensure you have power to the steering system. There's other means to do this. This is a very complex topic, but just to illustrate the functionality of the system, we wanted to put this out there for y'all, and we should have time for questions later. I'm gonna pass it over to Rich. He's gonna talk about the hoisted or lifted load. You're on mute.
On mute. Okay, thanks, Jonah. All right, so we talk a little bit about, obviously from a hydraulic standpoint, lifted loads are always critical safety functions. And so, the hydraulic system here we're assuming is similar to one we would use with a diesel engine. And obviously there's a lot of derivatives, but we're just going to replace the diesels, the prime mover with electric motor. So of course, what happens here in the safe torque off from the inverter is an instantaneous loss of electrical power to the motor. So the motor stops spinning. We have to vent that power. Once again, that's usually done in three-phase short. Can be a tremendous amount of current to deal with. And so that's something we have to often look at from an application standpoint. Different windings have different characteristics. The other thing, of course, when we shut off that motor, that pump is no longer producing flow. We will no longer have pressure. So like any good hydraulic design, we need to suspend the held load, right, with a pilot operated check, normally closed solenoid valve, counterbalance valve, typical hydraulic functions. And of course, we need to vent those pilot lines too. But the difference here is the STO event will turn the motor off really in milliseconds, right? So we will drop pressure very quickly. So from an inverter standpoint, so our RGVI Generation 2 inverter has two STO enable inputs. It's important to note in STO, the enable signals are positive, so they're low power DC. Removal of that input results in the safe torque off. So if we lose that signal, we're going to go into to STO. So for example, with a hoisted lift, we could have something that the machine controller doesn't like. It could be a number of different things. Initiates an STO, loss of enable signal, the inverter triggers, or it could be a device like a pressure switch, an angle sensor, a seat sensor. We're going to monitor bus voltage, that could trigger STO. Loss of motor feedback will trigger STO, excessive pressure in the system. So all these hard sensor bits can be an STO function or an STO trip. and can be designed into the system. And once again, it is a loss of a positive electrical signal. So the STO input bit is always like a 5 volt to 30 volt sourced input. And so loss of that signal will result in the safe torque. Jonah, I'll let you go back, talk about autonomous a bit.
Yeah, so 13.8, basically at a high level, we'll move through this quickly, but the ISO 13849 does not directly apply to vehicle autonomy. There's a lot of ISO standards that do apply directly, but the reliability attributed to certified devices can contribute to safety and autonomy. And the real thing here is you've removed the operator, so you no longer have that big processor behind that machinery. So then you're reliant, the machine has to be totally capable of providing safety in its operation, using different vision systems like camera systems, LiDAR, radar, ultrasonic sensing. It needs to be aware of its entire environment so that it's operating safely without a human element or a human processor, we'll say, behind the wheel of that machine. So key takeaways: functional safety is an involved process. There's a lot of resources required. So this is actually really interesting. I find it very interesting because a lot of the off-road equipment has evolved over the last, we'll say, 50 to 100 years. So there's been incremental evolutions of this equipment. Not all organizations have done a very good job of documenting how how the product should perform. So a lot of the initial upstart in functional safety is really documenting what the product is, what it should do, and then you can get into how to do it safely. So there are a lot of resources required, and this is a big entry point where if you don't have requirements for your products documented, that's kind of the place where you need to start, and that's really resource intensive. But in the end of the day, you just can't get around it. And then finally, each safety attribute or safety function needs to be evaluated. So, if you need to make sure that your blinker works when you hit the blinker switch to communicate to other people what you're doing, it comes down to the nth degree as far as ensuring safety and then identifying the different safety functions as part of your overall safety requirement specification. And just before we conclude, we've done a lot at Parker to ensure that we're supporting our customers in the off-road space. We do have a broad product portfolio really with safety in mind. So we can support our customers no matter what their needs are, whether it be gateway connectivity, displays, sensors. In the electrification space now, inverters, motors, e-pumps, controllers. We have our own object-based controls in the ICANN software that we offer to our customers, and then input devices as well. So Parker is a great partner as we move into these futures of electrification and functional safety. And then thank you very much for your time today. We appreciate it. And I think we have some time now for questions.
Thank you guys so much. First, thank you for tackling the challenge of breaking this down for us. Fantastic job. We've already got some questions coming in, so we're just going to jump right into the Q&A. And attendees, if you're holding on to a question, let it go. Click over to that Q&A box and get that submitted. Okay, guys, first question. We're just going to right out of the gate go with, what types of costs are associated with achieving ISO 13849?
So I'll take the first stab, and then Jonah can dive into. So, So one thing, from an inverter standpoint, right, which is a critical part of this, there is a significant cost in the controller capability, right? So adding an ISO 13849 function, it adds hardware, significant hardware costs, a little bit of firmware, but there is quite a bit of requirements, right, from the control board and the processor to support this. So that's just the hardware piece. And Jonah can talk a little bit about the investments, right, working with the consultants and the ratings agencies, which is really significant. Jonah?
Yeah, so the documentation is critical. Having dedicated staff with a focus on this is important. So most of the time you want to have a functional safety manager that owns the process. The ISO documentation really gives you a process structure, but it doesn't say if you do this, then you're safe, right? So then you need to interpret the recommended processes and then come up with a path that your organization is going to implement to ensure functional safety. And that's really the first step. But overall, it's very, very labor intensive, especially if you have to go back and capture all of your product requirements and the functionality and acceptance criteria for how your product is expected to perform.
Okay, great, guys. We're going to keep rolling. How is this different from an FMEA?
They're very similar. So your 13849 PLR it should be a multidiscipline team that defines what PLR you're at, what level you're at, and that's similar to an FMEA. Most of the time, you need to keep this. It's a separate set of documentation. They can mirror each other and they can parallel each other. And even when it comes down to the FMEA feeds into the DVP, well, you need a validation plan for your functional safety as well. So you need to be able to validate those functions that are a part of your functional safety. And you can merge the two. It is possible. But typically when you're seeking certification for a device or for a system, you want to maintain separate documents. You want to maintain your risk analysis and functional safety separate from your overall design risk analysis, which would be an FMEA. I lost audio.
Yeah, no, I think we lost Kathy.
It helps for me to not be on mute, guys. That's not you, that's me.
There you go. Okay.
Rich, was there anything you wanted to add to that response from Jonah?
No, we're good there. There's a couple more
Wonderful.
questions if you want to take a stab at those.
We're going to roll right through. Is this specific to off-highway versus applying to commercial on-highway vehicles or passenger cars?
Yeah, so I'll take this one, Jonah. Throw in some ideas if you want to. So, when we look at, what's complex for us, right, being in both markets, the on-highway side has the really driven by ISO 26262, right, which also affects, because we have hydraulic systems on highway vehicles, right? So we always kind of simplify things, 13849 for off-road. Now in some countries, right, off-road vehicle can be on an highway sometimes, right? So you may also need coverage of 26262. They are different enablements. 26262 is much more firmware intensive, where this for us is much more focused on the safe torque off. Of course, there's a lot of other things on 13849 that you can implement. But that's kind of how we see it, right? The two standards. The problem is we do have overlap, right? We have hydraulics on commercial vehicles, and then you're going to have the same capability, right, for the hydraulic system when it's on a truck. Jonah, anything to add?
Yeah, I mean, generally 13849 does not deal with traction systems. So the primary systems that propel a vehicle or provide tractive force of the vehicle is not governed in 13849. So that's where a lot of the on-road, because they're looking again at longitudinal control, the 13849 is not a best practice for that traction and on-road.
Okay, thanks, guys. And Rich, you just touched on this, but ISO 62621 seems to cover the same sort of thing for on-highway. Am I right? Says this attendee.
Yeah, there's a relationship. Jonah, do you want to go into any detail on that? I mean, they are overarching requirements.
Yeah. So I guess the family tree of functional safety is very big. That's what I'll say. I don't we don't have enough time, I don't think, to get into the functional safety family tree, but there's a lot of parents and children of children out there in the specification world.
Okay,
Yeah,
fair enough.
I think-
We've got so many questions here, guys. We're going to try to weed through some of these. Next up, is the STO signal always a physical signal, or can it be CAN bus?
Yeah, so I'll start off. So we always think of STO as kind of the old-fashioned red button, right? It's kind of the e-stop. It's you're cutting out a hard signal. You can achieve the same thing over CAN, right? You can do a torque zero communication to the inverter, right, to take power off, but it'll be controlled at whatever the deceleration, right, or whatever is programmed into the drive. But an STO is really a hard kill switch. So they're a little bit different.
Yeah, I agree. And you need to, if you are controlling it through CAN, you have a safety processor or some other control unit in that loop. That control unit then becomes a part of your safety function. So then you have to prove the system as a whole is capable of providing an accurate removal of that voltage.
Okay, guys, let me serve up one more here. What standards do I need to meet if I'm using hydraulic systems on commercial vehicle?
That's up to the
Why don't you
OEM.
start off that one?
Yeah, it's a good question. I think that you can the hydraulic work in PTO systems and ePTO systems can leverage 13849 because it is hydraulic work. Most of the time when we're developing products that are going into the on-road space, we're developing those with a 26262 because that's the common language in that market. And there's no value in us trying to retrain everybody that 13849 is capable for on-road. So most products are marketed as 26262 devices for on-road applications.
Great. Let me throw some more numbers into our number soup here. How does this standard work with ISO 21815?
Yeah, again, that's
Oh, no.
yeah, we'd have to pull up the family tree to dig into that one.
All right, we've got tons more questions here. Actually, I'm going to have Jonah lean in and see if there's anything here that we want to pull out of the list. If anything's jumping out at you, please feel free.
I like number 20, so I'll prioritize that.
Okay.
Okay. In that case, let me put that out to our audience here. For air quality regulators that are looking to require electrified off-road equipment in the near future, is the entire off-road industry voluntarily adopting this ISO standard? Should this standard be considered as a requirement for electrified equipment that receives incentive funding? It's a big one.
No, I would not put this as a barrier to receive incentive funding. The idea behind those incentives is that we're trying to electrify that equipment. The way that we should think about this when we're talking about the electrification of this equipment is these standards are now in place and become state of the art. So if there was an issue with safety on a machine, a device, the question is, did that OEM use state-of-the-art practices to manage the risk and safety? So, and that's what makes it, because there's not a regulatory, as Rich pointed out early on, it's not a regulatory requirement today. What it is considered, functional safety is considered a state-of-the-art best practice. And there's always safety through other means. And that's what, and again, because this equipment has evolved over 50 to 100 years, we don't want this equipment to be unsafe. And I'm not saying that other equipment that hasn't used this process is unsafe. There's always the safety through other means caveat where there's been other technologies that have been deployed that help to reduce the risk of personal injury or damage to property.
Great, thank you, Jonah. Let's put one more out here before we close things out today. Which standard should an electric truck manufacturer focus on? 26262 or 13849?
That's a great question. And we just had a global meeting last week, right? Kind of road mapping and a lot of discussion about yard haulers and material handling, right? Because it is in that gray area of, is it an on-road truck or is it controlled? So, Jonah, I'll throw it out at you too. But I mean, I think long-term, the safe approach is probably 26262. I think it's obviously the 13849 implementation will support a safe vehicle. It is definitely a gray area because we know that sometimes these vehicles do go out of the yard, but if they're in the controlled environment, we typically, the 26262, not required today, but we probably see it coming. Jonah, does that agree? Like I said, we just had this conversation Thursday.
Yeah. I'll go back to the statement of OEMs need to come up with their philosophy and how they deploy these processes and methods. And so really it's not up to us. Like, we're not being definitive in this discussion, first of all. Commonly, because traction is governed by 26262, that is the primary on-road focus for functional safety.
Okay, guys. Unfortunately, that does it for our time today. We've got lots of questions we can still put in front of our experts here today and get those out to you, get some answers to you later on. But that will go ahead and bring our session to a close. I'd like to thank our amazing speakers, Rich Nagel and Jonah Leeson, for their insights and expertise here today. Attendees, you can look for an email from us soon with access to playback and the presentation from this session. But please also feel free to visit oemoffhighway.com to check out more information on this topic and browse other topics in our bank of educational webinars. Thanks again to our excellent speakers, and thank you all for taking the time to join us. This concludes our session and day 2 of the OEM Industry Summit. We invite you to tune in for day 3 of the summit starting tomorrow morning at 10 a.m. Central. And you can register for these and any sessions that you may have missed at oemoffhighway.com/webinars. Until next time.
Thank you.
Thanks.